So the next speaker of this session is Francisco Chinesta. All of them know him calling Paco. Paco comes from Spain, he's born in Valencia, and is at present time professor of computational mechanics at École Centrale de Nantes. He holds the chair EADS Corporate Foundation International Chair and Advanced Modeling of Composite Manufacturing Processes from 2008 to 2012, and now he holds the ASC International Chair on Advanced Simulation Strategies. He is associate member of the University of Wales Institute of Non-Newtonian Fluid Mechanics, and in 2011 he was nominated senior member of the Institut Universitaire de France. And Paco is very well known for many domains, and I think one of the domains is the one of this.
Thank you very much, Olivier. First of all, I would like to thank the organizers, Javier and Antonio, for inviting me. It's a real pleasure to come back to my country. And I will speak today about the use of these computational vademecums that I will explain in some minutes in order to perform real-time simulation, real-time optimization, and real-time control of material processes and structures. So, we can define the state-of-the-art, the state-of-the-art, the present, the nowadays technology is we can solve some problems of interest, obviously, but for this we need to spend a lot of money in computers, and obviously we need to wait a lot of time. So this is probably the present. And what is the dream? The dream is probably treating larger parts, more realistic systems, computed very cheap. Yes, it's possible, and obviously very fast. So my talk is a small step, a real small step in that direction. So I will start with something that everybody knows, that is the standard numerical simulation. This is easy. You have a geometry, you have a model, a partial differential equation, and you have an unknown in general depending on the space and on the time. And in order to solve this, you need before introduce all the material parameters, introduce all the geometrical parameters that define the geometry of the problem, and introduce all the loads that applies in the system. And when you finish this, you push the button, the computer starts, and you wait for some minutes, some hours, some days, some weeks, and in biology, 2 years. So this is a PhD. You start, you run the program, and you come back to get your results at the end of the thesis. So, as soon as you compute your unknown field, you can compute all the variables of interest that depends obviously in this solution. Thus, it's not necessarily the solution itself. It's something that depends on it. And this is the classical numerical simulation. We can conclude, simple, yes, even easy if you have the code. But as soon as you change something, you need to compute again. You push again the button and you wait. So everything is easy, but probably is not the best solution. And sometimes you need to solve many times, because you are not only interested in one simulation, you are optimizing or making inverse identification. And in this case, you need to solve again and again. And each time, you need to wait. So, we are trying to solve this faster. And this is not new. Many time ago, there are some guys that prepare something that the name is the chart, the bac in French, el abaco in Spanish. And what is this? This is something that these guys that has a lot of patience prepare offline, and in this kind of artistic thing, they introduce all the possible solutions of your problem. And this is very nice, maybe better than the standard simulation codes. Because here you can introduce one parameter, the other parameter, and you have the solution. Okay, it's not good. You change. Okay, change. Please change, and you have the solution. You can compute. You can particularize online in real time. And this is something that is very nice. These charts are very useful, and even non-specialists in the industry can use it very easily. So my question is, charts is something classical, very artistic sometimes, but can we develop modern charts? This is a modern chart. I would like to introduce with my finger, choose the parameters, and obtain instantaneously in a smartphone or in a tablet the solution. This is the new age of the charts. So in my talk, I will explain you how to compute this kind of things. Easy. We are moving to the modern charts. What is this? I have my model. Oh yes. I have my material parameter, geometrical parameter, and apply loads. Yes. And I would like to compute what is the chart. The chart is the parametric solution. I would like to compute my solution at each position and at each time, as usual, but for any material parameter, for any geometry, and for any load that I can apply in my system. Wow, this is nice. I need this. I need to compute all the possible solutions. But probably it's not easy. Because imagine that you have only 10 parameters. 10 parameters is nothing. And that each one can take 10 values. This means that the total number of combinations is 10 over 10. And even for these guys that has plenty of time, is too much. Today, despite the fact that we have very powerful computers, I cannot pre-compute all the possible scenarios in my system. So, this is beautiful, but we cannot pre-compute all the possible scenarios because the number of scenarios explodes. This is the curse of dimensionality. Wow! So, this is all I finish my presentation because there is no discussion. Or maybe yes, we have some new routes in order to advance to faster and cheaper solutions. And the name of this is model reduction many families, meta model, surrogate model, the TOD, the reduced basis, and the PGD. PGD is not better than this. Is not worse than this. PGD is one member of the family of model reduction, and as I like a lot, as everybody knows, I will speak about this. That is one solution. There are many other things to perform exactly the same thing that I'm performing now. What is PGD? PGD has only two ideas. In my presentation there is only two ideas. In my life there is only two ideas. And maybe are not my ideas, so it's quite simple. Imagine that we're interested in solving the heat equation. very simple, one-dimensional space. Obviously, I put in blue the coordinates. The coordinates are the places in which I would like to compute my solution. Okay. And what is this in red? I put in red the parameter. In general, when you are solving your model, you introduce first the parameter and then you push the button of the button. Because if you don't introduce key, you cannot push the button. Okay, this is classical. This is 2D parametric. Easy. Can we perform better the first idea of my presentation? Not the after one, at least of my presentation. Is this. Key is no more a parameter. Key is a coordinate, like the space, like the time. Why? Because I would like to compute my solution at each point in a domain, at this time in an interval, and for each value of key in an interval. So for me, key is a coordinate in the space. Is a place in which I would like to compute my solution. So there is no difference. Maybe there is no derivative with respect to the key, but this is a chance. Okay? So, first idea of my topic. When you have parameters, when you have load, when you have something that you don't know or that can change, you establish this is not a parameter. This is a coordinate. First thing. But now my problem was 2D and now it's 3D. And if I continue like this, 4D, 5D, 10D, 20D, 100D, 1000D, off, maybe it's too much. Maybe, but there is another idea. So, the first idea is clear. The interest is impressive. This is my parametric solution. This is my chart. This is my modern chart. Why? Because as soon as you change, you particularize. You don't need to solve the game. Because you know your solution at this position, at this time, for any value of key in the interval that you choose. So, as soon as you change key, you don't need to solve the game. You need to particularize. To particularize this high-dimensional solution that you compute previously and you store in your code. Okay, this is nice. And another advantage is if my solution depends explicitly on the conductivity, I could take explicitly the derivative of my solution with respect to the key. And you are computing the sensibility fields. You know at what position sometimes you have an important derivative of your solution with respect to the parameter. And this is very important when you are computing or when you are making optimizations. And if you need second derivative in order to have Hessians, you compute second derivative and third and fourth. You can compute anywhere. Because now my solution depends explicitly on the parameter. Okay, wow, this is nice. And better, even in a stochastic problem, imagine that you know the solution at this position, at this time, for any value of key. You could, in a given point, at a given time, my solution depends on the parameter. And if the parameter is not one value, my parameter is a distribution, my output, my solution is not a value. My solution at this position and at this time has a distribution different to the one of the parameter, but that depends on the distribution of the parameter. So, in a certain manner, we are solving a stochastic problem in a deterministic way. And this is not so bad. But, the problem is very beautiful pattern, but the problem that was 2D or 3D, now we have plenty of dimensions. Okay, I'm very sorry, I will finish now the presentation. No, because there is the second idea. is the idea of Fourier, some centuries ago. He proposed the separation of variables. My solution that depends on x, t, and t, more than define a mesh, one per mesh that explodes with the dimension of the space. You know very well that 1D is easy, 2D, not too complicated, and 3D is in general complicated. I prefer to write that my solution that depends on space, time, and parameter can be written as a sum in principle until the infinite, but mathematicians say you, okay, don't worry, this converts very fast. Okay. So if this is the case, in this case means that this solution can be written as a finite sum of functions of space, functions of time, functions of continuity. These functions are unknown, and I need to compute. How to compute this? Imagine, we have my problem, my partial differential equation. I have my weak form, the classical weak form, the Gabertin weak form that everybody knows. I would like, when I start, I'm looking for the first term of this sum. I'm looking for the first. When I look for the first, I don't know this function. I don't know this function. I don't know this function. So the problem that was linear now is not linear, and I need to linearize. The simple linearization strategy is the fixed point, and the fixed point means I take 1t and 1t to start a random value, constant value you want. And in this case, as I suppose that this and this is known, I could compute x, because it's the problem with only one unknown, and it's linear. With this function that I just compute, and t, I compute t1. With the x and t, I compute the t. And I come back, and I have a nice loop here for the treatment of the nonlinearity, and this converts very, very fast. I promise you, very, very fast. Even like in Spanish, this converts very fast. And so now you compute the third one. When you reach the fixed point, this is known, and I compute the next one. I fix 2, I compute this, with this and this, I compute it, with this and this, I compute this, and I iterate until convergence. And this converts in general very fast and very well. And to do this, 8 years ago, with MATLAB and computers similar to this, we introduced a problem in 100 dimensions. 100. We put in each dimension 2,000 nodes. Oh my God! This means the equivalent of 10 power 300. It's incredible. The universe is 10 power 80. This is more than the universe. And I compute this in MATLAB in 20 minutes. Excellent. So we have a nice combination of only two ideas. One idea that is not the mind probably, and the other no, because it's Fourier. So I have not ideas, but both runs very well. I would like to compute model charts that are parametric solutions. First idea, all the parameters are now coordinates. Oh, the dimensionality increase. Don't worry. We apply the separation of variables. And we compute one term of this sum at this time, and we iterate in order to compute this, because the problem is nonlinear. So you need to introduce in your computer 2 loops, and this converts, even in this case, sometimes depends on the regularity of the problem, in some hours, in some days, maybe some weeks, but you compute this only one time in your life. Because when you compute this and you finish, you have a chart. And now we can do the chart. Which is the history of separator representation. Fourier, some centuries ago, Pierre Lavellesse, a little bit later, because he proposed imperative. Pierre proposed to separate transient problems as a sum of functions of x and y. And he called this radial approximation, and he introduced this in the famous Latin method that everybody knows in the world. There are some variants. Pierre also in mechanical problems introduced the separation of frequency and space, and Antonio separate the deterministic and stochastic coordinates to perform stochastic approximation. In my case, my group, my colleagues, Antonio, Elias, etc., we have three originalities. The first one is to treat multidimensional problems that are coming from the physics. Fokker-Planck equation, Boltzmann equation, and Schrödinger equation, problems defined with very large high-dimensional spaces. We apply this dimensional value. This is one. Second, problems that I define in a geometry, in a particular geometry, in a cube, or in a plate, or in a profile, I could separate the coordinates in order to solve a 3D problem with the price of 1D, or the 3D problem with the price of 2D. I will illustrate this later. And the last one is the Vademecums. The last one is the parametric solution. If you have a field that depends on space-time and a number of coordinates, please write this as a sum of functions of space, functions of time, and the product of all the functions involving all the coordinates. And like this takes time. This is maybe a little bit technical. Everything runs in MATLAB. And you compute this only one time in your life, and you have the chart. And when you have the chart, you can perform, and I will illustrate this, because all ideas I finish, I will illustrate this for real-time simulation, efficient optimization, efficient inverse analysis, and simulation based on. So I start with applications, and I come back to one application that Elias Puerto just introduced in the other room, but for the people that are in the room, this is real-time active devices in which I would like to have an active feedback, but very, very fast for training doctors or for performing this kind of surgical interventions at distance. And in this case, you need to touch and you need to have the real-time feedback. This means that for your eyes, for having the real-time sensation, you need 24 snapshots per second. Single. Holy. For the active, it's a little bit more complex. I don't know why, but when you take your finger and during 1 second you slide your finger on the table, there are 500 information going to the minds of people that have minds. And this means that in order to have real-time feedback, you need to solve in the order of 1,000 problems per second. 1,000 problems per second. But this is not linear. Yeah. It's isotropic. Sorry, it's not my responsibility. But you need to solve this 1,000 bytes per second. This is crazy. Yes, but we need. So our proposal, Elias, Antonio, the guys in that with me, Felipe, there is a very nice video in 1 second. We decide one day to introduce the law that the doctor is applying. And the point in which the law applies now are not parameters, now are coordinates. What is this? I'm computing the deformation field in any point in the river for any node applied in any position. My God, this is fantastic. Okay, what is the price we pay? I need to solve a problem in dimension 9. 3, 3, 3. Oh, this is not a problem for separation of variables. It's a sequence of 3, 3, and 3. You solve 30 problems, and you have the solution of the 9-dimensional problem. And this is nice, as Felipe proved in this video. This is Felipe coming there is exact similar simulations in Zaragoza, in the website. This is the liver of Felipe. I don't know if it but this is Felipe that manipulates this active device. And now, this is nice. This is nice, real real time. Why? Because we are not solving the problem, we are particularizing this solution. Wow, excellent, this is very nice. Okay, more applications. Another one. Plates, shells. This is placed in aerospace industry, in the composite structure. Why? Because we need to solve a problem in which sometimes there is not a plate and shell theory, and we need to solve the 3D in a plate or a shell in which the thickness is nothing. And in this case, we need to use in 3D simulations millions of nodes. We cannot solve this. So we decide to play the game, the separation of variables, and each component of the displacement field writes as a sum of functions of the in-plane coordinate times functions of the coordinate of the thickness coordinate. And a sequence of 2D problems provide the 3D solution. This is 3D solution at 3D price. This is a real nice solution for Spain because of the crisis. So we are paying less for the second. Now, and it runs very well. Write this. If I compute the 3D solution as a sum of 2D problems and 1D problems, the computing time is incorrect. If you are using a commercial code and you solve the same problem but using 3D elasticity, this is the computing time. Wow, nice. If you are looking for the modes is this function, the first, this function, the third, the second. It's very beautiful because the first mode is linear. This is play theory. The second mode is a little bit more complex, but it only applies in the border neighborhood because there are 3D effects. And there is another thing that is, which is the angle between the section and the middle plane. It evolves, and when the thickness is very, very small, you approach 90 degrees. With the first mode, you are moving from milling to kitchen. And there is not blocking. So this is quite nice. You can apply this to complex geometries, because even in this case in which you have not the sampling principle, and you have not a theory of plates, you can define the elastic properties as a sum of functions of the in-plane and functions of the thickness, with only 3 or 4 modes. And in this case, you can solve this problem, the 3D solution of this problem, this solution, but at the 2D price. You can apply this to laminates. You have many plies, and we are putting in this direction 100, 1,000, 10,000 nodes, because this only affects to the problem that is 1D in the thickness direction. You can apply this in shells. You need only 2 parameters, and apply the game at the composition with functions defined in the middle surface and functions defined in the thickness of the shell. And when this, you can compute this. This is a laminate. There are 20 plies. We are putting in the order of 500 nodes in the thickness, and we can solve this complex structure. You will compute this, the 3D solution of this, with a 2-dimensional cost. You compute very, very fast, something that is quite impossible to calculate. Alternative. You can apply this also to the fluids in this kind of geometry, because you have this flow. And in this case, it's like the 1,000 shells. Look at and now when you push, there is the cream that moves outside. And in this case, you need to solve the equation. In the resin part, you have stops. In the resin, in the fiber zone, you have dashing. We unify both in the Riemann equation, and we solve this by putting 1,000 degrees of freedom in 1 millimeter of the thickness, and you can compute very fast thanks to the separation of variables, and you can evaluate the flow of the resin, and you can perform this kind of solutions. Another one in process optimization is when we are performing this kind of extractants with composite materials. It's quite difficult because you are laminating and the thickness of the tape is 0.1 millimeter, 0.1, and the length is of the meter. And here there is not simplified theory, because this is multiphysical coupled, and you need to solve the 3D problem. And this is challenging, and in order to optimize the process, you need to obtain which is the optimal velocity of the line, which is the optimal power of the laser, in order to melt the polymer, the roller push in order to consolidate, and like this you can obtain the parts that exist in the future aircraft, like the Airbus 350. And this is challenging because this is 1 millimeter, and this is some tenths of meter. I'm doing a 3D simulation in which you are interested in optimizing the power of the laser, the velocity of the line, and there are also some thermal resistances because the consolidation is not perfect and there is a discontinuity of temperature through this interface. And we propose to create a Vademecum that gives us the temperature at this position, at this time, for any value of the thermal resistances, for any laser power, for any velocity of the head, for any orientation of the liners. We solve this problem by introducing 27 coordinates. A simplified model is this. We introduce this in a tablet that is used in Airbus. And this tablet, with your finger, this is a model chart, you can change any parameter and instantaneously you have the temperature distribution and two indicators, one for the consolidation and the other for the thermal degradation, because if you are applying too much power, you are degrading the result. And in order to appreciate the chart, you can appreciate you are changing any parameter, thickness, thermal resistances, the laser power, the velocity, and you can update immediately the temperature, and you can here notice the value of the consolidation indicator and the degradation indicator, and you can provide this kind of chart. And this is used even for non-specialist people in the industry. When you have this, you can also, after this, evaluate the thermomechanical coupling in order to define the residual stresses. And because the cooling is before the welding, and the heating is before the welding, and the cooling is after the welding, there appears residual stresses. And you can appreciate here by using a stochastic behavior law that this part at the end is in traction and this part is in compression. And when you do the mold with this profile of residual stresses, you can obtain finally the deformation of the part. That is very important in aerospace industry. Another example is the parametric 3D solution of frame structures that will be presented by Adrian Lake tomorrow morning in the reduced model session. And in this case, we would like to optimize this kind of frames. It is composed of 6 beams that are in this position in the aircraft, 320. And in order to optimize this, we need to choose the optimal flanges thickness and the optimal web thickness. The problem is each beam is composed of a lot of elementary beams, and each one has 3 degrees of freedom, 3 parameters for the design. And this means that in all this structure, we have 148 design parameters, and we need to try to optimize this as fast as possible. And this means, finally, we create, this is the 3 typologies of elementary beams. We create 3 abacus, one for each kind of beam, by considering the length, the 2 flanges thickness, and the web thickness as extra coordinates. And like this, we have a kind of level that I can assign in order to have any structure. So we have a kind of parametric structural analysis, and after when you compose all your Lego, you can assign this in the stiffness matrix, and you can solve in less than 1 second, and you are computing the 3D solution everywhere, in any point of this system. So it's not exactly the classical beam theory. Here we are using a kind of 3D parametric beam theory in order to compute this. So for multi-dice tomorrow, other than them in the room. And the last presentation, the last example, is using the reciprocity principle in order to perform real-time thermal analysis. This is a line collaboration with Antonio Elias. And imagine that you have the weak form of the heat equation. You see the form, yes? Okay, this is nice. Imagine that in this part of the boundary, the Newman part, you apply a flux Q1. In this case, you obtain a solution Q1. Imagine that you apply a source term Q2. You obtain a solution Q2. So you have for Q1 this solution, and for Q2 this solution. Now, I could assume that the test function in this problem I could take U2. And for the solution of problem 2, I could take the weight function coming from the problem 1. And I take this minus this, and I obtain this. If my problem is a steady state, there is no derivative, we obtain something that the name is the reciprocity principle. That I like a lot. Why? Because if I construct an artificial problem, 2, I apply Q2 and I obtain U2. I can perform this offline. And now online, you enforce a Q1, this integral gives you instantaneously the U1 in any point. And if you know U1, you can identify Q1. So by constructing an auxiliary problem, you can in real time predict the temperature in one position in order to control the process, or to identify the source term in U2. What is the problem? That in the steady state runs, but in the transient one does not run because the operator is not symmetric. And our idea was to move to the Fourier space. And when you move to the Fourier space, here you have the I omega, and the problem is symmetric. Wow, this is nice. This means that in the Fourier space we prove that reciprocity principle holds. And this means that if you construct an auxiliary problem by applying Q2 and computing Q2 offline, now online, as soon as you know Q1, you can compute Q1, or if you know Q1, you can compute Q1. You can control the process or identify the thermal sources. Difference is very beautiful. This is probably the last slide. And here is to prove that difference. This is a laser with power Q1 that is moving on the surface of this composite material. And we have a thermocouple in this point, and I would like to calculate in real time the temperature at this position. What is the idea? We apply a virtual flux in this point, we compute the thermal field in all this surface, obviously in the frequency space, and now in real time, because the reciprocity principle, you can compute the temperature at this position as a function of the time. This is the analytical one, and the dots are the one that we are computing. And this solution is better in this case because we appreciate the solution that we are computing, and here you have the time in the computer. You are computing 1 second simulation, 1 second of the process, in only 0.2 seconds. You are faster than the real time, and the only ingredient is using the reciprocity principle that applies in the frequency domain. And like this, you can identify, for example, the animations if there is a deviation with respect to the prediction, or if you know the temperature that you are measuring for in a thermocouple at a certain point, you can identify the source term indices. I will finish here. There are other applications where we are computing topological optimization. We have applied this also in shape optimization, in which you can compute a solution for any geometry. And now again, Felipe is moving the control points that define the domain, and in real time we are predicting the solution because previously offline we construct this kind of Vademecum that is the solution at this position for any position of the control points that define the geometry. And this is something that, sorry because it's not in the nice orientation, that provided me Elias, and this is a modern chart. We are looking at document, and we can introduce this kind of Vademecums in a PDF, and you will appreciate that in real time one student, one people in the industry could change in real time the parameters of the model, and immediately you have the solution. This is like a small lab for the use of students or other guys in industry that would like to understand process, and more than something that is absolutely offline and you cannot modify in the system. Now you can modify and evaluate the impact of something when you are reading a document. So probably it's not so bad for the education. So I finish on time, and the main conclusions are: first idea of the session, parameters are no more parameters. Parameters are coordinates. Which kind of parameters? Model parameters, initial condition, boundary condition, geometrical parameters, everything. Second idea, by making this my problem becomes multidimensional, but don't worry, don't panic. We have the separation of variables. And this means that in an iterative way, by solving low-dimensional models, I can compute the solution of a high-dimensional model in 20 dimensions, in 50 dimensions, or 100 dimensions in theory. Everything is not so pink like in mathematics. And finally, last point, when you have this Vademecum, please use it. Use it. Why? Because it's excellent, it's exciting, it's nice. And you can obtain real-time simulation, real optimization, and real-time control as I just proved. So, this is my presentation. I could finish by hesitation. PGD make promises, but remember there is no eternal promises. This is a word of Carla Bruni that I like.
So, for those who do not know Paco, no, you know Paco.